Good afternoon and welcome to the Computational Science Colloquium series. Today I have the pleasure to welcome my colleague and friend, Professor Ricardo Carretero, who's going to talk about dynamics, localizations, or structures.
Or something. Yeah, I'll talk about something. Well, thank you very much all for coming. It's really a pleasure to have half of my students that are here. I said, if you come here, you're going to see something cool. So many of you are here, so thanks for coming. I'm going to give a talk that is very fast-paced because I want to give you kind of an overall perspective of what my lab has been in terms of research for the past 8 years, 10 years or so. Okay, so I'm not going to go too deep into the math. I'm not going to go too deep into the computations. I'm not going to go too deep into the physics, but I'm going to have this tripolar disorder. I'm going to be somewhere between math, physics, and computations. And I would like to show how mathematics in the applied sense of the world, or the word, with A being a capital A, okay, so really applying the field, experimental physics, modeling, computations, all that stuff will be here. The whole shebang, it's about having a very complicated system. It could be a partial differential equation that has waves and things and turnings and twists, whatever, where you have a very intrinsic, localized type of solutions, they're called coherent structures, that have their own shape and size and form. So that instead of trying to describe the whole world, I'm going to just describe these jumping beams. So those jumping beams could be like solitary waves, they could be spirals, they could be vortices, they could be vortex filaments, vortex rings, it could be many different things. But I don't want to describe the whole world. It's going to be very difficult to describe the whole thing. It's going to be a partial differential equation in 3 + 1 dimensions, 3 spaces, 1 time. So try to do some sort of reduction so that I can describe these little objects on their own with their own parameters. Because those guys, this jumping, this could be a big one, a fat one, a thin one. And how do they interact with each other? That's the moral of the story. Dynamical reductions from complicated systems to easier systems. I'm gonna do like 3 parts of the talk. One is gonna be talking about solitonic filaments. So those are kind of speed humps. So like you have a speed hump in your system, and that speed hump might actually oscillate and try to describe it. I'm gonna also do a little bit of vortices. Those vortices are gonna have specific application, that is Bose-Einstein condensation. If you do not know about Bose-Einstein condensation, think about a superfluid. And then I'm gonna do, if I have time, a little bit of vortex rings as well, okay? So I'm gonna try to do all that. So that's the first part. The first part is the vortex filament reduction. The second part is the vortices. I'm gonna show even experiments and try to understand some of the dynamics. And I'm gonna extend this all the way to try to do vortex rings, okay? If I have time, I'm not gonna have time because I need to go over 92 slides and I talk fast, but still 92 slides in 60 minutes or 45 minutes, that's already very, very fast. So I'm not gonna be able to cover everything, but if there are questions, I can come back and I have slides to show for that. I don't have an agenda. If I just cover 3 of those 92 slides, that's okay. Ask me questions. As I tell my students, ask me questions, because if you ask me questions, I can stop and breathe. If you don't ask me questions, I just keep on talking. I don't breathe, and I then collapse, and you have to call the cops. So any interruption is welcome, so that I can actually take a little breather. All right? Okay. So let me just start with these dynamical reductions for solitonic filaments, and I'm going to show you a couple of pictures from actual experimental friends of ours. This is from an experimental setup on what is called a Carretero condensate. This is in Lecce in the south of Italy. And it turns out when they do these little microscopic systems, if they have 2 parts that they excite with different phases, they create a phase dislocation. And that phase dislocation turns out that it's unstable. That little line that separates 2 different phases of the Carretero condensate doesn't like to be just a single line. It just starts wiggling internally. It doesn't like just to be like that, it just wiggles. It's what is called modulation instability or snaking instability. So we are in the process of understanding in the experiments how this modulation of stability comes into play. One key question is, yes, they are unstable, but what is the wavelength of that instability? Is this going to create many wiggles, few wiggles? Why is that important? Because as time goes by, those instabilities of those solitonic filaments give rise to these dots here. Those dots are actually quantum vortices. So all these lines dissolve and eventually produce vortices. And that gives me also a leeway to why am I doing first filaments, and then I'm going to show you the dynamics of vortices. I'm going to do from both sides of the story. Before the vortices are formed when they're solitonic filaments, and they get destabilized, and then they create the vortices, but later I want to also describe vortices. Jose?
Will there ever straight lines
Will there ever be straight lines?
from the beginning?
At the beginning, there are straight lines, yes, sure.
Now you use lines, but there are straight lines and there are curves. So
You can frame the experiment with whatever you want. It's just if you start something that is just kind of straight, it's going to have a modulation of stability no matter what. So even if it's curved, and I'm going to show you because I have some circular stuff, and those circular stuff also become unstable to modulation of stability. Another interesting experiment here is an experiment from one of my collaborators at University of Washington, University of Arizona, and Brian Anderson. And he creates this condensate. I'm going to talk later about this condensate, but thinking about some sort of wavy system where you separate two blobs of the wavy system, and then you allow these two blobs to come to coalesce. And what you can is interference patterns. Those interference patterns are actually some of these wiggles precisely. So it's a stack of these wiggles. And in the experiments, they saw how these wiggles, they start not bending like this one, but they start bending in a different way, in a different time scale. And they didn't understand why. It seems that in order to get this type of bending, at least from our numerical perspective, it seems that there might be actually a vortex that was created there, and that vortex is created angular momentum, some rotation. So even straight lines that eventually will actually wiggle, the acceleration of the wiggling will be because you have a vortex, and that vortex actually bending the lines. And that, from a mathematical perspective, is a really nightmarish kind of thing, because you're talking about a one-dimensional structure interacting with a zero-dimensional structure. So you get a coupled PDE with an ODE. Nightmarish, but very, very cute and very interesting to do. This is a very, very rich platform to study PDEs, ODEs, and the coupling between them as well. Okay? That's the whole part of the story here, that is this very, very rich playground to play around with this type of distance. So this is how the reduction for a filament works. I have my filament that is wiggling. I have a notion of nothingness, and I have this high intensity speed hump of my partial differential equation. It could be light. It could be the position of more density. It could be the pressure that you measure or temperature. But the fact is, if transversely cutting this stripe, you get that has a solitonic structure. So the system itself, because of the nonlinearity, likes to have that as a structure that is a good structurally stable solution. That means that maybe instead of describing the whole partial differential equation, in this case will be a two-dimensional partial differential equation in space, plus time, I could maybe reduce this to, well, transversally, let's assume that the stripe is not changing its shape. It's just this speed hump, the transverse profile of the speed hump. And then the only thing that you need to capture is, where is the speed hump? So you see that I can go from a field that depends on X, Y, and T to just a position. Where is the filament located as a function of Y and T? So I go from a 2+1 PDE to a 1+1 PDE. I will be able to reduce in dimension by 1 by assuming that in the transverse direction, my primordial structure is not changing shape. Okay? And I'm going to give you certain examples later, but the idea is the following. Suppose that you have a partial differential, and there are many methods to do the reduction from the original system to a reduced system. And I cannot give them all of you. I'm going to give you the simplest one to understand. It's one of the simplest ones to understand. It's called an adiabatic invariance. it's something that is based on energy conservation. You have energy conservation, that energy conservation is going to allow you to do a reduction of the dimensionality as you will see here. So assume that you have this partial differential equation that depends on this field, U, that is x of y and t, okay? Then we want to project to a lower dimensional trial function that is just this transverse width, okay? So what you do is rewrite your partial differential equation in an energy format. You have the Hamiltonian or the Lagrangian. So you can actually, for this type of conserved PDEs, or what's called Hamiltonian PDEs, instead of writing the PDE itself, you can actually write the conservation associated with that PDE. Okay? The same for an ODE, for Newton's method, it will be T plus V, where T is kinetic and V is potential. You add them together, that's conserved. This is the higher order the generalization of that, where the PDE can actually be described by this conserved quantity, the Hamiltonian. Okay? So I have this Hamiltonian is given by some sort of nasty integral all over space of my field U, X, Y, and T. Then what I assume is that this is basically the big assumption, is that my full 2D solution or 2D plus 1 solution is really a 1D solution where the position is given by this X naught that depends on Y and T. And by just doing this reduction, because you're just projecting into this submanifold, you can actually control what the partial derivatives of things are of X with respect to Y. This is kind of a chain rule kind of stuff here. Okay? So now this one here, that this Hamiltonian that has a lot of partial derivatives, etc., I can reduce because I will be able to connect partial derivatives across the two directions and things that depend also on time, on how my wiggle is wiggling. Okay? So you put that into the system. Now you do this integral of the new Hamiltonian, but evaluated over your 1D structure or 1D stripe. And by assuming that there is a conservation of the Hamiltonian, so that the time derivative of the Hamiltonian is 0, you can actually get a partial differential equation for just the position of the wiggle. This is in very generic terms how you will do it. It will work for any Hamiltonian PDE where you actually have a transverse sort of trial function that you can actually project on. So this is the idea. Okay. So one of the examples that I'm going to show you is with this nonlinear Schrödinger equation. I'm going to introduce a little bit later where the nonlinear Schrödinger equation comes with the condensates. Here I'm just going to give you kind of the mathematical method. So I have this nonlinear Schrödinger equation with an external potential, and then in this case you have this wave that it's a primordial solution for this equation in 1D. This is what is called a dark soliton. Okay? So this is just a solution that separates two different sides of my domain that are in opposite phase. It could be light or it could be matter, and you have one phase and another phase, and there is some sort of transition between the two phases. That's given by this hyperbolic time. This is some sort of kink of my solution. Okay? You can plug this into the Hamiltonian of the nonlinear Schrödinger equation and get now an evaluation of the Hamiltonian using the position. And by just requesting that the time derivative of the Hamiltonian is 0, you can actually gather out of this a partial differential equation just for the solitonic filament. That is this X0. Okay? It might look complicated, but one beautiful thing about this one, it actually predicts the wiggling of this striping that I was telling you that is unstable. If you linearize this equation, done many linearizations before, this is just a higher order kind of methodology for linearization of PDEs. I can actually find this PDE here that is just the linearization of the wiggle. What happens with the wiggle with very, very small perturbations? It looks like a wave equation, but the issue here is that mu in this case is negative. So it's a wave equation with the wrong sign. That wrong sign is going to tell you that instead of like the wave equation, if you just have a little string and you perturb the string and the thing is going to wiggle, this is going to increase in size. So all the wiggins are exponentially going to grow. Okay? And this has been obtained in the past with other techniques, like perturbation techniques, etc. But the beauty about my equation here, it not only predicts at the linear level. This is a full non-linear equation that tells you not only how the wiggle starts to grow, but also when it's already over one, it can actually describe some of the dynamics because it has the full non-linear structure of the original equation embedded in here. It's kind of an extension of what you could do just with linear perturbation theory, but going one order or many orders beyond that. Okay? Let me just show you an example where this worked quite well. Okay, I do the same thing, but in radial coordinates. So actually, I get in this blob. So this is a blob now. It's a blob of light or a blob of quantum matter, where I have now the inner part to be one phase, the outer part to be another phase, and there is a transition region. This is the hyperbolic tangent. That's the hyperbolic tangent, but the hyperbolic tangent is in wave function. In order to describe the actual physical observable of the systems, you need to take the mod square of the wave function. And the mod square of the wave function is actually the density. You can see how the density is high, high, and there's an emptiness on density. The background yellow-red is the full run of the original PDE in 2 plus 1D. The green is the solution to this differential equation that looks in principle a little more complicated than the original NLS. 1 plus 1 dimensional. I gain dimensionality, much easier to integrate because I just need a one-dimensional system to go. And as you can see, as the thing progresses, time progresses, you see that the line will like to maybe oscillate inside because the line itself doesn't like to be bent. Because the line doesn't like to be bent, it just tries to expand, but the part itself is inside a potential, so it actually wants to go back. There is actually a position for this circle to be stationary. Here I did not start in the stationary. I started with a two height of circle that wants to expand, then goes on the track, and then comes out. Then out and in. On top of that, the line itself, it's prone to what I call with the modulation of stability, the snaking instability. You can see how this reduced equation can actually not only predict the breathing of the line, but also the wigging of the line in a very nice fashion. Where this approximation is valid up to, when the line becomes so wiggly that the line is not a line anymore, and you create vortices. So obviously, the equations that I'm trying to reduce from the original system to the reduced system rely on that might be, the hump, the tangent profile, the kink, the soliton. As soon as that soliton gets destroyed, my reduction doesn't even work anymore. It doesn't make sense to project the original dynamics onto my world because I don't have the piece to exist anymore. So at that point, once you get too much of a wiggle and you start creating that the transverse direction is no longer a soliton, these kinks, etc., then the approximation is no longer valid. I need to go to a different type of modeling. A different type of modeling is just, now I have the vortices, individual vortices. Let's try to study how the vortices interact with each other and try to get some sort of equations of motion there. Okay? You can do this for the nonlinear Schrödinger equation. You can do this for the Klein-Gordon equation. These are field theoretical models that are used in quantum field theory, blah, blah, blah. You can actually, I'm not going to do the equation. The relation is a very different equation. Okay? Still, you're going to see here how I'm able to describe the wiggling. In this case, it's not unstable. In this case, it's just stable. It will just wiggle forever, but the instabilities, the wiggle will not grow exponentially. So here I can actually follow for long times what the wiggle. You see the magenta line is my reduced PDEs, and the bottom color coordinate is my original PDE that is higher dimensional. And it does a really good job, these reduced dynamics, to describe the full dynamics of the system. Okay? So this is the idea of this reduction for solitonic filaments. Now I'm going to do something that have to do with vorticity, vortices. I'll change. Okay, so we're going to do this dynamical reduction, but now for vortices, and maybe if we have time, a little bit of vortex rings. But before that, I need to do a little introduction so that you know where I am, what system I'm actually picking here. I'm going to be talking about Bose-Einstein condensation. Okay, so this type of matter was predicted almost 100 years ago by Bose and Einstein, but it was not until 1995, until the late 1990s, that it was able to be created. The issue is that you need very, very, very cold temperatures. The reason that you need very, very, very cold temperatures is because each individual particle, from a quantum perspective, is associated with what is called the Royal wavelength. And that Royal wavelength has on the denominator of P is the momentum, M times V. So if the temperature of the condensate or the matter gets lower, 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 meaning that the kinetic energy of the system is lower, kinetic energy is not proportional to V, but proportional to V squared. So temperature is proportional to V squared. At least temperature is an increasing function of the velocity. If you reduce the temperature, you reduce the velocity of all those little beams, and so that the wavelength grows. What happens is that wavelength is of the order of the spacing between the atoms in my matter here. Because I have this wavelength that is of the order of the interspacing distance, I finally get a synchronization. And all the particles of the system synchronize at a quantum level. The analogy here, if you want, is that if Bose-Einstein condensate is to matter, what laser is to light. So let's stop just 30 seconds. What is light, laser light? So what makes laser a laser? I mean, just start asking you. I said, oh, intensity. No. A floodlight from the stadium will burn me much more than this laser. This laser is not burning me. So it's not intensity. Oh, color, monochromatic. No. Usually lasers are monochromatic, but I can have monochromatic light as well. That is not laser. What makes a laser a laser? All the photons inside the laser are synchronized at the quantum level. And that means that you can have like tunneling effects because everything is just synchronized. So think of a block of matter that is synchronized at the quantum level. So all these atoms, all these molecules, all these whatever I'm taking in the condensate, they are all synchronized at the quantum level. So it's like a giant macro quantum particle because all of them are just synchronized. Okay. This is what I'm describing, this matter. So it's very important because you can actually do experiments and do very, very high precision measurements. For example, you can do super precise gyroscopes, super precise gravitometers. And one of the reasons is that you can actually manage matter at the quantum scale. This is huge, managing matter at the quantum scale. So this is good. So that's the type of system that I'm interested on, and I'm actually collaborating with some of my friends on this system. This is the equation that describes the condensates, is what is called the Gross-Pitayevsky equation, and it's nothing what I just wrote before. Mathematicians call it the nonlinear Schrödinger equation. Physicists call it the Gross-Pitayevsky equation, but it's just the same equation. Okay, it's an equation for this field phi that is complex, that describes the wave function of the condensate. You don't like to talk about wave functions, and wave functions trip you out. It's okay. Just do the mod square of that complex field, and that is just your roll, your density. The density, how many atoms per square millimeter or per cubic millimeter are there? Okay. One of the nice things about the condensates is that they have to be grown in a magnetic elevator. Just they have to be levitator. Because if I just build them in a vessel, in a glass container, whatever, the container itself will be super hot. Okay? The condensates will become condensates when the Broglie wavelength is of the order of magnitude of the interseparation distance. You know what is that temperature? Nanokelvin. Okay? Super, mega, super cool. So I cannot produce any vessel that will be cool enough to maintain a condensate. I put my condensate in this vessel is hot and it will evaporate. The only way to create condensates is to levitate them with a strong magnetic field. Have strong magnetic field in the x direction, the y direction, and the z direction. And if you don't believe me that you can actually levitate matter with magnets, just go to Google and put levitating frogs magnetic fields. There are videos of people putting frogs, and frogs don't have a very huge magnetic moment, very small magnetic moment. And you see the frog like just floating. And in that space, it's just magnetic fields. And these I'm talking about very, very small droplets of the size of a micron. So I can very easily levitate drops of a micron that have a much larger magnetic moment than actually frogs that are made of water, basically water. Okay? So the nice thing about these potentials is that I can squeeze the potentials in all the three directions. So it's a huge playground from a mathematical perspective. I can have all the three components of magnetic field equal. So I have a blobby, chunky BEC. Or you can flatten it, very strong magnetic track in this direction. So I have a pancake. Two-dimensional structure. So I can actually run the element in 2 dimensions. Or you can actually squeeze, not squeeze, and have a one-dimensional stripe where I can actually do experiments and mathematics in 1D. So very rich. And you almost anything that my weird mathematical brain will make here to exist, I'm going to do this very funky thing. I can actually ask my experimenters, can you do this? Of course we can. We just put this, not almost anything you can care to imagine will be able to be carried out in this condensate. That's another reason why condensates have been really good at doing the bridging between theory and experiment, because you can do almost anything you want in this condensate. Let me show you some experiments. In this experiment, there is this trap. It's a parabolic trap given by the magnetic potential. The potential is not really parabolic, but you just use the very center of the magnetic potential, and then you approximate the bottom by just parabolas. But in the magnetic potential, there are coils. It's really non-linear, very ugly. But I'm just doing the very, very bottom of the potential. Okay? So this is 2D. I just when you flatten in this direction, I have a pancake. So one dimension is gone, and I'm just looking at a pancake BEC that is trapped in this 2-dimensional parabolic trap. Okay? And this is the little blob that is contained in this parabolic trap in 2 dimensions, and it's photographed from the top. Okay? This is the size. This is around 100 microns, and the timings here are going to be of the order of milliseconds where they take the photographs. And you see something funky here. There seems to be a hole. Okay? And you see what happens to this hole as time progresses. That hole is rotating. That's actually a vortex that is rotating. Why is the vortex rotating? This vortex is actually, do we have things to write on here? So we have these, not very good, but this is the potential trap, the external magnetic trap, and then you have the cloud. And in the cloud, thank you. You're going to set up a vortex, and that vortex is sort of an emptiness. The vortex, the twister twists, pushes mass outwards because of centrifugal force, and it just depletes the density there. Okay? And you have this little vortex that is in here. And the question is, why is this vortex doing stuff instead of just staying quiet? That has to do with breaking the symmetry of the system. If the system is completely flat, density-wise, force-wise, everything is isotropic, I put something in an isotropic solution in an isotropic medium should not move because I'm not biasing anything. What happens if I just induce a change of density because of the external trap? Well, I change the density. What happens? I include this, I induce this asymmetry, and the asymmetry will make my beast to move, right? Now the question is, why is it moving like that? Okay? So if you have a potential, and you put a little billiard ball, and then you do this, billiard balls just go down, right? This one is not going down. This is the density. So this is my inclined plane. It's actually going perpendicular to the inclined plane. The first thing to note is that this is not a billiard ball. This is a bubble. It's emptiness. So when you have a glass of wine, a bottle of wine, you incline it like this, the bubbles don't go down, bubbles go up, right? So in principle, bubbles, this is a bubble because an emptiness should actually go up. The problem is that this guy is actually rotating. When you have rotating things and you try to push them, those guys go perpendicular to the force that you're applying. It's called the Magnus force. So you don't know a little bit about physics. So if you have something that is rotating and you try to move it in one direction, you will go in perpendicular. If a twister is coming at you, you just blow out of the twister because you don't want the twister to come out to you. You're not going to blow the twister or reverse the twister. You're going to make it go perpendicular to what the force or velocity they're applying to. And that's the reason why these vortices are rotating, because it's feeling a force that is perpendicular to the gradient, and the perpendicular to the gradient here, as you know from calculus 3, will be simply a curve of constant height, an isocontour, and the isocontour of this paraboloid, it's a circle. Okay, so you can apply calc 3 to actually get that the orbit of a vortex inside the trap will be actually a circle. What happens if you put two vortices? Well, you're going to have two effects. Single vortex wants to precess, is called precession because of this Magnus force inside the potential because of the gradient of the density. And then vortex-vortex interaction. I don't know what is a vortex-vortex interaction, but there are going to be two ingredients going on here. Okay? Let's see what happens with this vortex dipole. Very boring. Seems to be nothing happening. So somehow the forces, these two types of forces, are balancing each other so that you are at the stationary steady state position. Okay? So things that I talked to my ODE guys and my dynamical systems guy, a steady state solution. Even the modeling people have been talking about all these fixed points and stability. Okay? So you see that this is actually a steady state solution of balancing forces of my jumping beams there. All right. Other experiments, slightly different initial conditions in the experiment. This is what you get. You get this type of circular motion. If you remember your analysis of fixed points for ODEs, if this is a neutrally stable fixed point, a center, and you perturb a center because the system is conservative, they're not going to shoot out outwards or inwards. If you're neutrally stable, you just rotate around. That's what you do when you have conserved systems, like a pendulum. You just perturb the pendulum oscillates, no friction, because it's Hamiltonian. So any stable steady state in a Hamiltonian system is not really stable in the sense that perturb goes back. You just perturb never goes in, but never goes out. It just maintains its distance from the perturbation because you have no dissipation. Maybe that's what we see here. So this is just screaming at me, hey, professor, this is really a fixed point that is neutrally stable, that must have eigenvalues that are just complex, so that you get just rotations. Okay? We will see in the modeling if that's actually true. In fact, depending on how you argue the initial conditions, you can actually have these dipole. Just look at this angle, minus 45, and then just iterate this guy. So you see that it's now horizontal. So there seems to be two different rotations. One rotation and like a rigid other rotation. So period 1 or frequency 1 and frequency 2. This is what is called a quasi-periodic behavior, quasi-periodic motion. It's a motion that involves two different frequencies. One frequency and then another frequency. Can we understand this from the modeling's perspective? That's the whole idea. All right, let me introduce in more detail what I mean mathematically by these vortices. So I have my nonlinear Schrödinger equation. Let's forget that there's potential. So I have no potential. I have just an infinite ocean of condensate. And I'm going to try to set up there a solution that has the following shape. It has a radial profile. It has a frequency. This has to do with just quantum mechanics or energy of the system. The system is just in time, the real and imaginary part rotating with a certain frequency. Forget about that one. The most important term is this term, is the phase. This is denoting a S being an integer. It's a phase winding. So if I start with phase 0 here, as I go, this is phase pi over 2. This is phase pi, 3 pi over 2, phase 2 pi. And because I made a full jump of 2 pi, cos of 2 pi x, 2 pi plus x is the same as cos of x, continuity. Oh shit. This tells me that just because this equation is quantum in nature, so it has to be written in complex, the way that I can change phase is by integer multiples of 2 pi, because I cannot go half a pi, because then the phase will not match. The phase has to match. And that's why things are quantized in quantum mechanics, because of boundary conditions. A box that has certain boundary conditions. In this case, the boundary condition of the rotation that the angle has to be modulo 2 pi. Okay, so I can actually have a vortex that has this phase structure that exactly has a phase jump from 0 to 2 pi. Or you can have a jump from 0 to minus 2 pi, or any integer multiple. So the charge x could be any integer. 1, 2, 3, 4, minus 1, minus 2, minus 3, 4. And then the reduced equation that you get out of inserting this into the original system in polar coordinates is a partial differential equation for the radial profile. This is the radial profile of the vortices. This is what is called a boundary value problem. At 0, the vortex has to have vorticity 0, density 0, and at infinity, the density has to be back to the density of my original flatness. Okay? When you solve this equation, it's a partial differential equation. There is no solution that you can write analytically. You have to do it numerically or with approximation. You get this type of vortex radial profiles. Charge 1 minus 1, charge 2 minus 2, charge 3 minus 3, etc. The higher the charge, the more angular momentum, the more the atoms are pushed out, so you get a deeper hole. It turns out that charges 4, 3, and 2 are actually unstable. So one vortex of charge 2 will eventually split into 2 vortices of charge 1. And you can look this at from energy consideration. This is more energetically favorable than having like this. Okay? So always in physics, you will go to more general energetically favorable states. So this is my beast. Phase and attention. Okay? You can actually do some mathematical work to actually work out what is this frequency of precession rate. To have this is presetting at this frequency of precession, and you can compute it mathematically. It's a function. Is this function? It has to do with the charge. So the charge is going to tell you if you go to one side or the other. If you're getting very close to the edge of the condensate, this is the what is called the Thomas Fermi radius. Things get very fast. You start to rotate very fast, because you can see that as R gets close to RTF, the frequency goes to infinity. Okay, I will tell you later if I have time why. Well, no have time. I'll tell you another day why. But once we get closer to the edge, they go faster, and that's a nonlinearity, right? The same as a nonlinear pendulum. The linear pendulum has a constant frequency independent of the amplitude. This doesn't have a constant precession as a function of how far you are. There is this nonlinearity. That nonlinearity is going to be responsible for some of the bifurcation structure that you will see about the solutions later. So it's very important. Okay. All right. What happens in a vortex scenario? So if you paddle in the boat, and just along when you paddle, you're going to create in the wake of the paddle a plus and a minus vortex. Or go to the swimming pool, do that. What happens to these two vortices? This vortex rotates these two vortices. This vortex rotates like that. So it's pushing this guy down. This guy is rotating in the other direction. So it pushes this guy down. So this one pushes in this direction, this one pushes with the same velocity. So a plus and minus vortex will always go in parallel to each other. If you have now a plus and a plus, this guy pushes this upward, this guy pushes downward. Where can you have a motion where these velocities are perpendicular to the line of sight and opposite? Circle. That's what happens with planets when you have circular motion. And that's how you see plus minus go parallel, plus or minus, they just go in circles. Okay, and this is what you see. I'm not going to show you the movie because I don't have time, but you see exactly. You see them rotating depending on the charge. All right, and I can quantify these effects. So now that I can quantify these effects, let me put them together. So these are finally my equations of motion for my vortices. I can put many vortices into the system. 10, 20, 100 if you want. Each one is going to have a precession. Its position is going to depend on where it is, and it's going to be rotating and precessing with a precession frequency that is proportional to 1 over the distance squared to the origin. And there's going to be a vortex-vortex interaction. This vortex-vortex interaction is precisely what I was telling you, plus minus and plus plus. Okay? It's embedded in here. And you see that now you have this system of coupled differential equations that each position of each vortex is coupled to the background cloud and to the other vortices through this sun. But it's just a simple, ordinary differential equation on the vortex position. I'm not integrating this ugly mess of a PDE that I started with. This is just a very cute, very simple ODE for the center of the vortices. Okay? It turns out that it has two conserved quantities. This ODE itself has a conserved quantity that it corresponds to the energy, and a conserved quantity that can be labeled as some sort of angular momentum. Not going to go too much in details, but if you have taken dynamical systems, you know that if you have 2 degrees of freedom in an ODE, you cannot get chaos. The only way that you can get chaos is with 3 equations or more in ordinary differential equations. So if I have 2 vortices, I have 4 equations, because each vortex has an x and a y. So 2 vortices, 4 equations, minus 2 conserved quantities means that I only have 2 degrees of freedom. The maximum behavior, most complex behavior that you can get out of 2 degrees of freedom is 1 frequency with another frequency, quasi-periodical motion. So in order to get very beautiful chaotic dynamics for these vortices, I will need at least 3 vortices. The 3 vortices will be 6 degrees of freedom minus 2 conserved quantity. I get an effective 4-dimensional system, and 4-dimensional systems could actually bring chaos. Okay? But not this one, as if you are just taking pairs. Beautiful. Okay. I have my ODEs. What is the fixed point of these 4 ODEs? It's just equate the right-hand side equals to 0 and see what the fixed points are. Well, it turns out that when you do that, there is a fixed point. There is this fixed point. There is this very, very special distance where the interaction is strong but not too strong. If you go too far out, the precession gets very accelerated because of this steepness here. Okay? If you look very close to each other, the vortex-vortex interaction dominates. Far away, the trap, the potential dominates. Somewhere in the middle, you have a sweet spot where you have this fixed point. This fixed point can actually go to the ordinary differential equation, linearize around it, and when you linearize around it, you can actually find its frequency of oscillation, and that frequency of oscillation determines that if the system is stable or not. In this case, it's stable. I have this frequency is always positive, so e to the I omega t, omega real means rotations. If the omega is complex, I have e to the I omega t, I complex times omega complex is real, and we get explosion. Okay? In this case, I get just simple motion that is neutrally stable motion around the steady states. And this is exactly the 2, I already knocked down 2 movies that I showed you at the beginning. The vortices that were split, they were exactly at the right distance. And if you have a symmetric perturbation, you have this very beautiful motion between the 2 guys. Okay? Nice. So this is the other one that we saw, the other movie that we saw, is that we have kind of two frequencies, right? This frequency and a body and a hard body rotation of the whole system. How can we understand these dynamics? Mainly, if you're careful, you'll see that the distance of this vortex to the origin is smaller than the distance of this vortex to the origin. So instead of doing a perturbation that is symmetric with respect to the sweet spot, suppose that I do an asymmetric perturbation. What will happen in that case? Well, you can set up. You can just do set up of having one at a radius 1 and one at another radius, or 1 and R2, or 1 and R2 be different. You can actually look for co-rotating states in a co-rotating frame. and you're able to find steady states. And those steady states, you can again perturb them. They have the frequencies. You can compute the frequencies. The frequencies are actually real, so it's also stable. Okay, and this is the pictures or the trajectories got from the experiments. And you know what are those? They look. The first one I kind of make up, that is this plus a rotation. But this is very complicated. I don't know what that is. But if I measure the centers from the experiment and put it in my ODE, and I compute this rigid body rotation that I can from my original ODE, I can deflate my solution or mount myself in a co-rotating reference frame. That in the co-rotating reference frame, I should already see that me. I mean, you're seeing all these spiral loops, right? I'm only seeing circles, okay? So if you mount yourself in the right reference frame, this should only be circles. By circles, I mean ellipses. And this is exactly what it is. Once you know where you are, you just move yourself in the right co-moving reference frame, co-rotating reference frame, and you can see that the ugly pictures that were before in the experiment can be very well understood as just this, but asymmetric, so I have a little circle and big circle on top of a rigid body rotation, and they could be understood that way. And the dynamics of the reduction tells you precisely these frequencies. So it's a perfect match between not only the PDE. Remember what I'm doing here. I have a physical system that is described with an equation that is a part of the differential equation. I'm doing a reduction to a lower dimensional system, and I'm doing a dynamical system to find fixed point and stability. And then from this, I go all the way to my original physical system to see if they actually match. And they do match, as you can see here. One of the most striking behaviors that we notice is not when you have a plus and a minus. Is when you have a plus and a plus. So I'm not going to go into the details. Okay, these are polar coordinates for a plus and a plus. The reason for going to polar coordinates is if you have a plus and a plus, one vortex likes to process, a plus vortex likes to process, a minus vortex would like to process in the other direction, but plus processes, and a plus on their own rotate. So everything comes together. I cannot have this sweet spot balance because everything is rotating in the same direction. The only thing that I can do is find steady states in co-rotating frames. So now I'm doing a plus, but I'm going to analyze it in a co-rotating frame. So if I set myself in polar coordinates, and the only thing that I actually measure is not the angle of one and the angle of the other one, but actually the difference of the angles. If you do the difference of the angles, then any solution will be rotation invariant. So I actually factoring out this possible co-rotation. Okay. So after setting myself into this co-rotating frame, again, not giving you details. If you linearize your system around the equilibria, you get that the square of the frequency is this guy. Small r, real. Eigenfrequency, real. Oscillations. I get very close to the edge of the cloud. This guy goes to 1. This is rescaled to 1. This guy wins. This is negative. The square of a negative means that the number is complex. Complex, real-time state explosion, instability. There has to be a point where the radius, after that radius, my orbits become unstable. That's what we call a bifurcation, where an intrinsic change in the stability of the fixed points ensues. I go from stable to unstable, a point of instability. Okay? And this is the type of bifurcation that you're going to see in this experiment. It's what is called a pitchfork bifurcation. The plot is stable to a certain radius. I'm plotting here the angular momentum. The angular momentum has to do with how far away they are from the center. After that point, the plot becomes unstable. Why does it become unstable? Symmetric one that I was telling you about that gets blurred exactly at the point of bifurcation where this guy becomes unstable. Still the stability out of the symmetric state, and you create two asymmetric states: the small big and the small big asymmetric states. And those two are stable in what's called a pitchfork bifurcation because it looks like a pitchfork. Okay? Now it will be very interesting to go back to the experiments and actually see this. Let's try to think how we are going to be able to see this in the experiment. Keep in mind that the experimentalists cannot place the vortices where they want. They just put turbulence, they cool it, and suddenly you have plus plus, you have plus minus, you have plus plus plus. They don't know where they're going to be. And this guy sent me hundreds of these timeframes of different vortices. If you see this, how will you match to the actual experiment? This is the key. How many times have you gone to the street and have you seen pencils upside down, just standing on the street? How many times you have seen pencils standing like this? This is an unstable steady state. This is stable steady state. Do you see in nature unstable steady states? No, because if you start them, they're unstable and they're going to topple away. So I should not be able to see in any of the runs from the experimentalists dipoles that are larger than the critical radius. And if they are larger, they have to be asymmetric. And that's exactly what we did with hundreds of different shots from the experiment. Every single time that we got two that they were rotating. And remember that this is stable. So even if it's a little bit perturbed, they're just going to perturb. So it's going to be a wiggle. And this is this example. But if they were larger than the critical radius, that is the dashed line, I will never be able, these guys, to see that they just co-rotate, because that state is unstable. Okay? And this coincides very well. You want to play tricks with three, you can play tricks with three. The bifurcations becomes really ugly. I'm just plotting here the primary bifurcations. If I plot the whole full bifurcation, you won't see a thing. It's just a big blur of many lines of stable and unstable. Just looking at the main one. You can do it with four. The four have the same type of bifurcation. Big four it has a subsidiary bifurcation because there are all the structures that bifurcate away from it. All the crazy shit going on. Okay? Can I see this in the experiment? Yes, you can. Whenever you see three vortices that never overtook one the other, it's small. And you get these three vortices, and they are wiggling a little bit, three, because they never start with exactly equilateral triangle, because the experiment doesn't start with exact, but still, it's stable. And when the triangle is too large, then you can see that they don't preserve their angular position. One takes the other. And then I was able to find a four. It's a four state. So it's four below the critical radius where these guys are dancing, because it's a stable steady state and still was able to be captured by the theory. Okay, so beautiful match to the level that I can actually check. Okay, I cannot check the precise dynamics, etc. This is the pictures that I got from the experiment. I can do it from the level of PDE, and the PDE is really an excellent match. But I wanted to go back not only to the PDE, but back to the actually original experiment. Jose, 5 minutes. You can do even funkier things. You can actually grow vortices on donuts. And if you have a donut, you have curvature. And that curvature induces some other changes. Okay? And then you can have all sorts of funky things. So this, I really like this work. This work was done by one of my master's students that just graduated last semester. And we're about to publish a paper on this. So it's about orbits of vortices in these non-Euclidean geometries. Pretty funky because you need differential geometry, and the Laplacian of the original NLS becomes what's called the Laplace-Beltrami operator. It gets pretty funky, but it's very cute. Now, do not have time to go over this. Let me just show you the upshot in the last 4 minutes and 59 seconds that I have to show you what happens with vortices that you elongate in 3D. So vortex 2D, you elongate them in 3D. Vortex line twister, grab this twister and connect the twister with itself. It's like when you do the smoking and you do the smoke rings. So those are the smoke rings for condensates that in each transverse cut, I have a vortex, like a 2D vortex, but in the transverse cut of the ring. Okay? This is experiments, blah, 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 blah. This is how two vortices interact with each other. Two vortex rings interact with each other. Really beautiful behaviors here. This is what is called leapfrogging behavior. Okay, this is a full 3-dimensional run using sophisticated numerical techniques to integrate this system. Okay, but actually do my lovely magic math and reduce all these systems to 4 variables. Z1, Z2, R1 and R2 can set up a system of 4 ODEs, mega ugly, because the interacting potential is a Jacobi-elliptic type of very ugly function, but I can write it. Now the question, if I run the ODE, it's just 4 ODEs, no space. How does it match my original leapfrogging behavior? And this is this picture. Again, I'm placing myself in this leapfrogging. I'm placing myself in a co-rotating frame. So in the not co-rotating, co-traveling frame. In the co-traveling frame, the leapfrogging is just periodic orbits. You can see what is it? The black line is the ODE, and the dark line is the PD for different radii of the vortex ring. Very, very, very nice prediction. And here, to integrate these black lines, no problem. Take like a microsecond in MATLAB. The red lines take GPU computing or whatever, it takes a few minutes. Okay? So it's not exact, but you can get very quick results. And you can even say things about the stability. That's the beauty. You can intrinsically say something about the stability, not only the orbits. Right? And with that, I will close. I'm not going to tell you about the numerics, any of that. So I'm just going to, I'm going to close that and just say thank you very much.
Thank you, Ricardo, for that tour de force.
Very first.
Any questions? No, now he's breathing.
You didn't have any question. I'm dying here.
I told you 5 minutes because I don't want to die before.
Thanks. I appreciate your help. What's up?
Were the dashed lines unstable diagram? Pitchfork you showed.
In the pitchfork, usually we plot red or dash as unstable and blue or solid as stable. Yes. So the red was unstable. Yes, yes. That's normally how it's plotted.
So you linearize, you go to your reduction, and you look.
I don't linearize. That's the thing. I reduce because I like my nonlinear. I'm a nonlinear guy. I cannot get out rid of my nonlinear.
You reduce and you're looking locally.
In some places, yeah.
But then you say, okay, go back and I match. But if you don't lose anything by just looking locally.
Yeah, you lose many things.
Okay.
But I'm not going to tell you the things that I lose. That's not the way the world works. Well, I'm going to just tell you one, and it's a fun one to actually look at it. Let's look again at the movie. In this case, I reduce my OD by assuming that my rings were rings. They're not moving from a ring. Rings in the first place stable. Careful. Do you see any sort of the rings doing some sort of wiggle? They're actually unstable. So you do this for a while. Those are called Kelvin waves. The rings themselves are going to start wiggling, and eventually they're going to get destroyed. I'm going to shoot all the vortex rings that I cannot capture because I assumed that they were circles. So provided they're still circles, my theory is good. Once they're not circles anymore, then I will have to have a new theory that includes Kelvin waves. This theory doesn't include Kelvin waves, but it's possible. I should be able to actually include Kelvin waves. It's going to be more complicated because I need more degrees of freedom. I need the degree of freedom now of my Kelvin wave. And each mode, the 1 mode, the 2 mode, the 3 mode, the 4 mode, will induce a new ODE in the system. So I want need to integrate 4 differential equations, but 6 or 8 or 10 describing more and more things. So yes, this is not the panacea. I'm not going to create the entire planet with these solutions. It's provided the reduction is valid, so that what I'm describing still within my realm of my trial function, I'm good. Yeah, so it's a good one.
But now let's thank our speaker.